We start this lecture with section 16.16, which is a very short section on an introduction to pericyclic reactions. Unlike previous reactions that we've encountered that have ionic or radical intermediates, pericyclic reactions have no intermediates at all. These reactions are concerted, which means they happen in one step. They all involve the movement of pi bonds around a ring. The first category of pericyclic reactions are cycloaddition, which is going to be the major focus of our discussion today. Here we have a diene and an alkene, which is also called a dienophile, and reactions move pi bonds around a circle, like so. The product of these reactions is a cyclohexene. In this reaction, we gain 2 sigma bonds and we lose 2 pi bonds. In an electrocyclic reaction, we start with a hexatriene derivative, and electrons also move around in the circle, this time forming 1 sigma bond and losing 1 pi bond. While we won't talk about this reaction in the book, and you won't be tested on it, it is worth noting this pattern so you know which problems not to practice at the end of the chapter. Lastly, in sigmatropic reactions, we have three bonds moving around in a circle, and this time we have no net gain or no net loss in sigma bonds and pi bonds. Section 16.7 focuses on the cycloaddition reaction called the Diels-Alder reaction. As stated on the previous slide, this reaction involves the addition of a diene to a dienophile and creates a cyclohexene ring. On this slide, the X substituent is simply placed to show you where the substituent is relative to the alkene. This sigma bond is this sigma bond. The potential energy surface of this reaction shows that the cyclohexene is lower in energy than the starting materials, and that there is only one transition state and no intermediates. But there is a detail of this reaction that we are not used to discussing, and that is its reversibility. There are thermodynamic considerations that we must take into account when heating the Diels-Alder reaction. The Diels-Alder reaction proceeds to the products until you get to very high temperatures. At temperatures of about 200 degrees and higher, the reverse reaction occurs. Why should a reaction go to its starting material when heated at higher temperatures? The answer here is entropy. Require that the equation delta G equals delta H minus T delta S. The equation tells us that lower enthalpy favors the formation of the product, and often the entropy term doesn't matter because there is not a significant change in entropy. But here we have 2 starting materials going to 1, and so entropy matters, and it overrides the delta H term at high temperatures, causing the reverse reaction to occur. Now let's talk about the structure of the diene and the dienophile. We'll start with the structure of the dienophile. Dienophile is a term that means diene lover. We'll focus on the dienophile first. One thing to know about the Diels-Alder reaction is that it proceeds more rapidly and has higher yields when the dienophile has electron withdrawing groups. Why is that? Well, we won't go into the details. If you're interested more in molecular orbital theory, which is section 16.8, it's because the LUMO of the dienophile, which is what participates in this reaction, is lowered in energy, making it closer to the energy of the HOMO of the diene, which is the molecular orbital that also participates. It is worth noting that when the diene is disubstituted, stereochemistry is preserved. So if the dienophile is cis-substituted, the product will be cis-substituted too. If the diene is trans-substituted, the product will be trans-substituted, and here to an enantiomers form. An interesting aspect of the Diels-Alder reaction is that alkynes can also serve as dienophiles. Here the product has 2 pi bonds in the cyclohexadiene ring. One is a residual pi bond from the alkene, or from the alkyne that didn't react. Next, let's look at some examples. Note that the first example we have butadiene, but it's drawn in its S-trans conformation. We need to redraw it so that it is in the right geometry for the reaction. We also need to reorient this other starting material to have the carbon-carbon pi bond facing the diene. We draw our circle of electrons moving around the pi system, and that gives us a product that has cyclohexene, and it also has a second ring because we never broke the bonds to the second ring. We only broke that pi bond. We didn't break the sigma bonds. In the second reaction, we again need to reorient the diene to put it in its S-cis conformation. Then we need to reorient this pi bond so that it's in the correct orientation. Notice that the groups here are in the trans position, the acyl groups are. And because they're in the trans position, that means that we're going to have 2 products that are enantiomers of each other. There. Next, let's talk about the diene. Recall that even though the diene will be S-trans in its conformation most of the time, it will only react in the S-cis conformation. Therefore, dienes that are locked in the S-cis conformations will react much faster than those that can freely rotate. Cyclopentadiene is shown here as a molecule that will react very fast. In fact, it will react with itself to dimerize. Can you draw that product? The answer will be in the notes when it is uploaded. I think it's also in your book. The diene on the right, which is drawn in red, is unreactive in a Diels-Alder reaction because those pi bonds can never be in the S-cis conformation. Let's look at an example of a cyclopentadiene ring reacting in a Diels-Alder reaction. We need to reorient the diene so that it's favorable to the dienophile, and we get a product with 2 rings, one from the cyclopentyl group and one from the cyclohexyl group. You can also draw this as a flat structure as long as you use your stereochemical indicators. When there is one substituent, or if you have two substituents with a cis conformation on the alkene, you get what is called endo addition. An example is shown here with cyclobutadiene and cis dicyanoethylene. When the methylene groups point up, the substituents favor the dienophile pointing down. The exit product is not favored. Why is the endo product favored? Well, it is a little hard to draw. In the transition state, the electron-rich electron withdrawing groups of the dienophile stabilize the pi system in the diene. Here are a few representations of this product. Your book presents this better than I can draw in figures 16.18 and 16.19, and those are within section 16.8. I recommend that you take a look. Let's do some examples of drawing the product with some cyclic dienes. First, you need to rotate this molecule furan so that its pi electrons are facing toward the dienophile. And how do we know that there's a diene and a dienophile? When you have this alkene that's got two electron withdrawing groups attached to it, that's your identifier that it's the dienophile. And furan is the obvious diene because it has an S-cis conformation of 2 pi bonds. Here we draw our 3 arrows again, and I'll give you a minute to pause your video and see if you can draw this product. Welcome back. It's important that if you have your molecule in this configuration, that you make it clear that the substituents are pointed down. And so you can do that by adding the implied hydrogen atoms. You can also make that clear by drawing the molecule in 2 dimensions with stereochemical indicators. Now, before setting up the second example, I'm going to let you pause and see if you can get through this problem. Okay, welcome back. Let's set up this reaction. There we go. This slide and the next focus on regiochemistry. What happens if you have a diene and a dienophile that both have one substituent each? Without knowing about electronics, you could write either one of these sets of products. However, only one example in each set is correct. To determine which of each set we form, we need to look at the partial positive charges and partial negative charges on the dienophile and the diene. How do we match the delta plus and the delta minus? We need to look at the resonance structures of the diene and the dienophile. In the dienophile, in the first example, we have an electron donating methoxy group at the 2 position of butadiene. Pushing electrons into the carbon-carbon pi bonds gives you a lone pair on carbon 1, which also possesses, therefore, a partial negative charge. In the dienophile, we can push electrons into the cyano group, giving a partial positive charge to its carbon 1. To its carbon 2. Next, we need to check that the negative and positive charges align. In this case, they don't, so we need to rotate one of the molecules so that they do align. With these 2 molecules, here I'll rotate the dienophile so that now we have negative and positive charges overlapping. And that's how we know to build our diene. And so we get the methoxy groups and the cyano groups on the opposite carbons of the cyclohexene. Let's do one practice to wind up today's lecture. Here I've given you the diene in its S trans conformation. So the first thing we want to do is rotate that. Oops, let me back up. The cyano group is the same as before, so we know that its partial positive charge is on carbon 2. And then in the methoxy compound, I'll use a different color here. Its partial negative charge is on carbon 4. Now I'm going to scoot that, well, here. Now we can see that the partial negative charge and the partial positive charge line up, so we don't need to do anything to rotate these molecules further. But I'm just going to add the arrows in green to connect these to, I'm going to redraw them first. And that gives us our product. So this winds up today's lecture. Have a good day.